Welcome to the Cosmic Pie Podcast, Season 4, Episode 2. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota.
Yep.
We do have a chat feature that is running, so if you're watching this in real time, please feel free to send us any questions or comments or anything else, and we'll take a look at it and stop what we're doing and try to answer the questions to the best of our ability.
Well, if it's relevant anyway. I mean,
where can I get the cheapest gas in North Dakota?
Yeah, we're not going to be able to answer that one.
Well, let me go to the website and I'll check. Gasbuddies.com or something. Yeah. Anyways, the other thing we always say, of course, Robert, is what?
That the opinions and things so forth that are expressed herein are those of my Wayne and myself, and not a reflection of the opinions of the University of North Dakota, Department of Physics and Astrophysics, or anyone else. It's just us.
Just us. A lot of stuff going on related to space.
Absolutely. There usually is. It's just most of it flies under the radar.
This is a very, very exciting year. And we'll get into it in a second, especially when you think of human exploration of outer space. This is going to be the year that kind of sets off a whole new era in some sense of human space exploration. If everything goes well.
If everything goes well.
Which hopefully it will. So we'll see all that. But of course, haunting my daytime dreams is an object we've been talking about since...
Yeah, sooner or later we'll get away from it.
Since July the 1st. You want to take a guess what this object is, Robert?
Let's see. 3-Eye Atlas, maybe?
Yeah, Comet 3-Eye Atlas. Yeah. And there's been another study that has come out recently, and it's by the Breakthrough Listen group. Remember, these are the people who received a lot of money from the rich Russian billionaire. I guess if you're a billionaire, you're rich, right?
I hadn't heard about that, but
yeah. So he supplied money for a lot of different things. He's one that's behind the idea that you could build a little tiny probe to try to send it off to like Proxima Centauri using lasers to give it a good push, if you like.
Well, that's not as far-fetched an idea as
it's not. It's
it
not.
Sounds.
It's not like it's like bonk or something, right?
Right.
I mean, it's legitimately trying to push the engineering of today.
Which we should be doing.
But, of course, it's all private money because the government's not going to touch something like that probably.
Right.
Just too much speculation, and the high chance of failure is there. So, yeah, one of the things he's also looking at is can we detect any signals from advanced civilization, so-called techno-signatures.
Right.
And one way to do that, of course, is the way that we've been doing it for many years. I think this first started, 1960?
Something like that.
With Frank Drake.
Frank Drake, yeah.
Listening, or eavesdropping on any potential civilization out there that might be broadcasting at certain wavelengths in the radio. Didn't work out. And so today, the modern incarnation of that would be the SETI program.
Right.
And people to search for extraterrestrial intelligence.
I was going to say, they're still doing it.
Yeah, they're still doing it. No detection, of course. And they've had detections, right? I mean, it's not like they never see anything, which would be, talk about a boring job.
Right.
So, I mean, are you sitting there at the computer with your feet on the desk waiting for a signal and you're snoozing and you got a side hustle or something to keep you awake during the, other times when you're not there? I mean, it seems like it's...
The issue is that it's got to be a repeatable signal.
That's the thing. So they find things and they search them down, and Seth Shostak has written a great book called The Alien Hunter, which I've read.
Okay.
And in it, he describes a signal that the SETI people picked up, and they didn't know where it was. It seemed like it was moving at the sidereal rate, which would be the rate at which the stars move across the sky because of the rotation of the Earth. And they double and triple checked everything and tried to, where did it come from? Did it come from known satellites? And at first, they didn't see anything that would be coming from that was put up by us. And eventually, they discovered it was coming from the Soho spacecraft.
Oh. Yeah.
Which explains why it was going at the sidereal rate, because that's not in orbit around the Earth.
Right.
And unfortunately, because that would have been something spectacular, right? It turned out not to be alien technology. And, I mean, there's been other signals that come, something gets detected, and then, like you said, it's a one-time thing. And it's like it has to be repeatable. The famous one in this line of research is the WOW signal.
The WOW signal,
right?
yeah.
From Ohio State, if I remember right.
Right.
So they picked up a blaring signal one day, and somebody was looking at the chart recorder back then.
Yep.
and saw the large signal and wrote "wow" with exclamation mark beside it. And so it became known as the wow signal, except it was only picked up once.
And nothing else.
Nothing else. As my understanding, they were doing a survey at the time, so they quite don't know the exact location on the sky that the antenna was pointed at. They have a general rough idea, I believe, and it never repeated. So, I mean, what is it? Some people say, oh, probably it's just earthly things, maybe something coming in on the side lobes. So a radio antenna, the way they function, if you're not familiar with it, you have sort of the main sensitivity. It's usually forward of the main antenna. We call that the main beam. But then some stray signals can be picked up on the side. Those are known as side lobes. So the antenna is also sensitive a little bit on the side. So that's why, if you see the image there on the far right, that's the 100-meter telescope at Green Bank in West Virginia, I think it is.
West Virginia.
It's West Virginia. That if you don't want people walking around with cell phones and using them. Because even if you're on the ground, you might say, well, how can that dish pick it up? Well, it can pick it up from the side lobe. It's sensitive off to the sides.
Right.
There's some sensitivity. And that signal then can be picked up by the very sensitive detectors that they have hooked up to the radio telescope. And that can, of course, actually, that can destroy the equipment because the signal will be so strong.
I was about to say, cell phones operate on more than this 100 milliwatt that this paper is
Yeah,
talking about.
so if you're picking up a really strong signal, it could be so strong it can do some damage to your equipment because they're tuned to be very, very sensitive. It's almost as if you have hearing aids and you crank them up, if you can do that, so that they're extremely sensitive because you're listening to something very far away, just a faint whisper, and then somebody, unbeknown to you, snuck up behind you and yelled at you with a blowhorn.
Right.
That's the same kind of thing here. What you're talking about.
Or you're using night vision goggles and all of a sudden somebody throws on a spotlight.
Yeah, that would that would definitely overwhelm your goggles at that point. So there's always been, a surge, and this stuff has gone over. Do you realize, if you think of the 1960s, and there's been spotty sort of looking since the 60s till we got into probably the late 80s, early 90s, where it's become more routine.
Right.
Doing this sort of systematic search of all different types of stars, not only stars like our sun, but other type of stars as well, hoping to find technosignatures. And there's been nothing detected yet. And with that null detection, as we call it in science, you can say a lot about that. For example, the chances of having advanced life forms in our solar system is pretty low.
Yeah. I think we would have picked them up.
Okay. That doesn't exclude, of course, any type of bacterial type of very small number of cell like structures, because they wouldn't be able to build a radio telescope.
Right.
And it excludes dolphins. Because if you had life form that lives underwater, like a water planet,
Right.
it's hard to imagine that they would develop the skills to build a radio telescope.
Because radio waves are blocked by water relatively quickly.
So there's an issue there. Or imagine if you lived on a planet that was completely cloud covered, really thick clouds constantly. You wouldn't even know about the stars, would you?
Well, you wouldn't.
And if your planet was massive enough that maybe there's chemical rockets just can't reach escape velocity to get above the atmosphere, then there's no way of knowing that there's something beyond
Right.
the location you're at.
And then, as I like to point out to people, another possibility entirely is people always go, oh, so they wipe themselves out after a certain technological stage. Well, that's not necessarily the case. We're going radio dark right now, and we clearly haven't wiped ourselves out. But we are directing signals to where they're going. We're using fiber optics. We're using all these things that keep the signal from going out into space. So that may be a possibility of why we're not detecting anything. They don't need it anymore.
And the other thing, too, is when these signals go out into space, they spread out. They're not focused like the best laser you can ever construct.
Right.
And they're collimated, the small little spot beam. That's not what occurs. So the radio signals spread out, and they become weaker and weaker and weaker with distance. And so it becomes harder and harder to detect, of course. If you're far enough away, it might become to the point where you can't detect it, even if you had the technology like we have today.
Right.
For example. And the other thing is the interstellar scintillation that occurs, where you have ionized material moving around, and that interacts with the radio photons and can attenuate and shift their frequencies even, and so on.
Right.
And so, and things are not, it's not like it's a perfect vacuum. It's not like that at all, even though we kind of think of that in some cases when they're doing, simplifying
Well,
type
for
of
human
thought process.
purposes, it is a vacuum. But
Yeah, as they say, that vacuum is not empty, folks.
right.
It is full of wonderful stuff.
Oh, yes.
So that makes it much, much harder, to detect things or things to detect us. Now, this latest study that was just published not long ago, it's actually a preprint, so we have to be aware of that. It's looking at radio signals coming from Comet 3I Atlas to see if there's, it gets down that whole line of a thought process. If it is an alien spacecraft, are they communicating with something?
Mm-hmm.
And therefore there are transmissions that are occurring. And if there are transmissions, can we eavesdrop on those transmissions? And so they monitored the comet for a period of time and said that they got all the way down to about 100 milliwatts in terms of power output.
Right.
And they said there are no signals stronger than that 100 milliwatts. And for comparison, that's 10 times weaker than your cell phone.
Mm-hmm. Yes.
So still no signal from the comet. That doesn't mean that there's absolutely no radio signals, because it could be weaker than the sensitivity. There's always limitations on your equipment.
That's weaker than the radio signal you're broadcasting because you have a non-zero temperature. So, yeah.
So that's another thing that goes against this being an alien spacecraft. Of course, unless they're radio quiet, right? You could
Unless they're
always
radio
say
quiet.
that they're built that they won't transmit until they get well beyond the solar system. Then they'll do burst transmission, and all the information will be sent back to planet who knows what.
Right.
Right? And you populate it by who knows who.
Right.
Locate it who knows where.
Who knows where.
Anyway, so it's an interesting kind of exercise to do this.
Yeah.
In fact, it pushes a little bit our technology. Like, can we make it even more sensitive than that? How do you do that?
How do you do
We
that?
can build a bigger radio dish, but that takes a lot of money. But the other thing is you can have it more advanced amplifiers and filters and so on, electronic part of things.
Right.
And that just, brings back a payoff in the future when we use the equipment to do other things.
Well, it makes for a better radio transmitter and receivers because we can use less power to transmit the signal.
Yeah.
So, yeah.
Exactly. Now, Robert, here's a question for you.
Okay.
Where would you not want to be if you got sick?
I would not want to be in space.
Imagine getting a real bad cold in space and your nose is plugged up and
Yeah, because it won't run.
it's not going to drain, right?
Yeah.
'Cause
It's not going to drain. So the pressure is just going to stay there and build.
that must be terrible.
Oh, yeah.
That's why you isolate astronauts or cosmonauts or whatever they are
For weeks.
for
ahead of
weeks
time.
before ahead of time, so make
Yeah.
sure you're not going to take up anything like that. But this has been on the news the last little while now. I guess you've heard about it independent of this. Is the fact there's somebody on board the International Space Station that is not feeling well, as far as we know. Now we have to preface this, the fact that the medical information is kept private,
Right.
unless it's a major thing, right, that would impact the mission or life or whatever. And so all we know in this case is that one of the members that are on the International Space Station, one of the astronauts, had a medical issue. They were dealt with the best they could on board the International Space Station. Like, you're not going to do open heart surgery on the ISS.
Oh,
right?
no.
Imagine on weightless what that would be like with the blood and stuff. I don't
Oh,
think
Lord.
How would you ever
think of that?
if you're on a long-term space flight,
Yeah.
I mean long-term, let's say 10, 20 years heading somewhere, you'd have to have like centrifugal force. A thing would better rotate to allow you to have that faked artificial gravity so that you can control the flow of blood like in an operation. And there must be a way you have to,
Right.
have to deal with those situations potentially.
I mean, that is one of the problems, as I understand, for long-term space habitation is the fact that your heart atrophies because it doesn't have to pump as hard
Yeah.
against gravity.
That's why you have to do a lot of exercise. They spend many hours a day just exercising.
Just exercising. Yeah.
You have to, right? Because of that. But anyways, in this case, it's something they can't deal with on the International Space Station, and they can't wait until the normal time for this crew to come down from the International Space Station during normal crew rotation. They actually have to bring them down early.
which tells me it's probably something pretty serious.
It has to be.
Yeah.
This has never been done before. This is the first ever
Right.
what they call medical evacuation from the ISS. Now, this is due to occur tomorrow.
Oh, okay.
So the last
yeah,
I heard
January
is
14th,
4 p.m. Central Time tomorrow on January 14th. They're supposed to depart from the space station, and then by the time they land, it'll be after midnight. So that's January 15th or whatever.
Right.
But yeah, so tomorrow is supposed to be the beginning of this, and I don't know if we will ever hear what actually happened. Like I said, this stuff is private.
Right.
Probably depends on the individual if they want to release that to the public or not. But we'll see what happens. So. Thankfully, it's the International Space Station. It's not a Mars-bound spacecraft that
there
has
would be
left
nothing you could do with
that
that.
have left Earth 3
Yeah.
months ago and has 3 more months before it reaches Mars. What would you do then?
Oh, I hope you've got good doctors because it's going to have to be taken care of then. There.
So that's definitely a risk. How do you mitigate that risk? I mean, what do you do? You take doctors with you, people who are trained in the medical profession. In fact, that's what occurs on most of these flights since the space shuttle days.
Right.
They've been able to take a large enough crew up. But what you're really limited on what you can do when you think about it, and there's no getting back to Earth quickly. Because even when you arrive on Mars, let's say 3 months later, there's no way to get back. You have to wait probably about a year and a half or so before you get back at the earliest, so the alignment to be better.
Right.
So they minimize the time between Mars and Earth transit.
The only caveat on that is if we allow for the testing and creation of the nuclear rockets, which would not be limited to the Hawkman transfer orbits and could just fly directly back. But even
then you're talking, I think, 3 months.
yeah, 2 to 3 months.
Now, how do you get around this a little bit? Well, easy. You take Dr. McCoy.
Take Dr. McCoy with you. Yeah.
Just don't ask him to do anything else because
Yeah.
I'm not a bricklayer. I'm not a computer technician.
Right.
I'm not a carpenter, Jim. Damn it, Jim. I'm a doctor, not a carpenter. Anyways, the other thing, what you could do is you can screen people as best as possible. And there is screening here in this case. And whatever screening was done never
showed whatever
issue all of a sudden appeared, right?
One possibility is they broke a limb or something. They got in a bind or something in moving around. And
can you set that in orbit? I mean, if you had
probably could
you
do
had
a
the
preliminary
equipment.
set, but
And then if you think that, hey, I wonder if they got like even an X-ray machine that they could do a portable
right.
scan of that. I never heard
these are
if that's the
things.
case. It'd be interesting to do that.
Yeah.
I mean, if you lost a leg, you just bring a 3D printer with you, and
Yeah.
and while you're there, can you add a few extra toes so I could swim better?
Right.
Little
webbings in between.
Make my foot a flipper.
Eee.
Not a dolphin.
Oh, okay.
And I guess we shouldn't be laughing. This is serious.
This
right?
is serious. I mean, something has clearly gone wrong.
But the interesting question is, what do we do for longer duration missions that are not in orbit around the Earth?
And
That's very
on the
interesting.
lines of Dr. McCoy, the answer is you've got to create some kind of medical bay to handle more serious things.
You'd have to have an automated, at least as much as possible, operating room, which actually can do heart surgery and all kinds of technical stuff.
Yeah.
You'd almost have to. And
just
probably
have to.
artificial gravity, I would assume, right? Because I would assume the problem is really astronomical, if I can use that word. If it's weightless environment.
Yeah. If it's weightless, like you said, there's going to be problems with blood flow and
All
things
that
like
stuff,
that.
yeah.
So this is the first, but it's also indicative of our problems with this.
Well, the other thing, I mean, it's one thing to be in Earth orbit, and this is near Earth orbit too. You're only a couple hundred miles above the Earth. It's pretty low orbit type of stuff here. Is what happens when we go the next step further and end up on the moon.
Right.
And even if you're on your moon, your normal rockets, you could probably get out of there in a few days, but you're talking 3, 4, 5 days. So if it's a real emergency,
You're just stuck.
you're stuck. But then you're on the moon, so you're in 1/6 gravity.
Something like that.
And you'll be able to then maybe perform these detailed operations and have the equipment set up. Imagine like a base in Antarctica. But even Antarctica, they medical evacuate people. That happened, I think, last winter, if I'm not mistaken.
And in fact, when I was at Case Western Reserve University, one of the professors there in my department was in charge of ANSMET, and the Antarctica meteorite finding teams. And I was like, I want to go. And he's like, he was finally like, Robert, do you understand with your breathing problems? If we had a problem, it's 3 months before we can get you out.
Right.
You know?
You just told the world you got medical issues, Robert.
I know, and
You
I
doxed yourself.
yeah, well, it's okay.
Okay.
But you know, he was adamant on the point that no, I'm afraid we couldn't take somebody like you because while you've never had a medical emergency with it, if you did,
Yeah, there's no way to help you.
you're done.
Yeah. Well, there was someone not long ago, if I remember, they had cancer, breast cancer, they were diagnosed, and they had to be evacuated.
Right.
And they went through a lot of hardship. I mean, it's really risky for people to go in there and get you in the middle of the night in the wintertime in
the
Antarctica.
wintertime, yeah.
And you got to wait for the weather to be just right to evacuate you out of there.
Right.
So they can do it, but they don't want to do it.
Oh no, it's costly.
And why would you do it too if you're going to be able to like survey people, in other words, do a detailed medical examination,
Right.
and eliminate all the ones that have underlying conditions,
Yeah.
you know, and why would you pick people to go down there that have issues?
Yeah. And the same thing is true for these types of missions into space.
Yeah.
You screen them as hard and as well as you can, and if
We
it's going to be a problem, you
and
say
we
no.
we talked in the past about even just migraines. If you had somebody who's fully qualified, who gets migraines, and you had another person who's fully qualified that doesn't, which one are you going to take to go in space?
I'm going to take the one without the migraines.
Because you know they might not be able to handle what's going on around them for a period of time when a migraine comes on, and that could be at a time when there's an emergency on board that you need everybody,
Right.
and this
All hands on
individual
deck.
is incapacitated because of the migraine.
Right.
You just don't know when things happen like that, so why take the chance?
And the answer is you don't. I
You
mean,
don't,
you go with even a slightly less qualified person who doesn't have medical condition like that.
for sure. Now, here's the big exciting thing that's happening this year, and we've talked about it a little bit in the past, but as we get closer and closer to the magic day here, things are going to ramp up tremendously.
Right.
And it all starts this Saturday. I believe that's
wow.
the 17th of January. And
Okay.
that's the date when the whole stack, the Space Launch System, the supporting Artemis 2 mission, is going to be rolled out of the Vehicle Assembly Building down at the Kennedy Space Center in Florida and head to the launch pad.
Interesting.
Now, that's when they will start hooking up all the equipment and do their testing and make sure everything's going to go right and do their dress rehearsals on the pad and so on to get all ready to go. And the launch is supposed to occur, and you can see the launch windows there, early February. So if you have time off in February, you want to get down to the Kennedy Space Center. And if you lived in North Dakota and you're able to get to Florida in February, there's a lot of sort of benefits that go with that besides seeing the launch. But notice that the launch windows, there's periods of time in February, and then we skip to March, and then in April. And of course, there'll be ones beyond that.
Why are they a month apart?
Because you want the alignment. Yeah, exactly, for the moon.
not being silly.
I see you are. But for those who don't know, you got to have the right alignment for lighting on the surface of the moon and things. And the moon takes a month to go around once, hence the month comes from the word moon.
Yeah.
And so, so every month opens up these windows of opportunities where conditions are right that you want to be able to launch. Now, this spacecraft did launch a couple of years ago, the rocket that is.
The rocket did.
With no one on board. In fact, they never had the environmental systems all on board. And one of the things that happened was when they examined the capsule when it came back, the Orion spacecraft, that it had some issues with the heat shield.
Right.
It was more erosion of the heat shield than what they expected. And this is all for testing, and it's coming back at an incredible speed, like somewhere like 25,000 miles per hour when it hits the upper atmosphere. So it's coming in at an even faster rate than like the shuttle would come down, or a rocket that's coming from the International Space Station, a spacecraft, the Dragon.
Yeah.
So you have to, there's extra things you have to deal with here. And there is some small number of people that want NASA to send up another flight to go to the moon and back, but unmanned, just to check that heat shield to be 100% sure that it's going to be okay. And then also check the environmental control system to make sure they're going to function properly before you send humans up on the spacecraft.
And I get that, except things like the heat shield, you're never going to get 100% sure. You know, we've had evidence of that happening, you know, before now. So I'm not sure I buy that argument. And, you know, you get it as good as you can get. You test it, you test it, you test it. And then at some point you have to go with it.
Well, I think there was a lot of deterioration of the heat way more than expected, like
Yeah.
to the point where people became concerned.
Right.
And I think a part of that, I think, is the history of the space program.
Right.
And that involves both the Challenger and the Columbia. If you look in the accidents that happened there, they seem like they were preventable, both of them.
Both of them, yes.
And if something is preventable, that means it's human error, essentially, at some point along the decision tree that caused these issues that ended up catastrophic
Failure.
And that's something they want to avoid, of course, with this. So hopefully everything will be okay. The engineers assure us that everything should be okay with the heat shield on its entry, and hopefully the environmental systems all works. Everything's functioning normally for them there and back. And the whole premise of this mission is kind of like Apollo 8 back in, what would that be, 1968, if I think?
Something like that, yeah.
Where they, it was a push, I think, to get to the moon, of course, first. The United States did that in July of 69. And there was, I guess, if I remember the history right, reading about it and hearing about it, that the Soviet Union, the CIA, I guess, or whatever intelligence service, had told the American government that the Soviet Union was on the verge of launching a really large rocket capable of sending humans to the moon.
Right.
And the United States, of course, following on the speech made by John F. Kennedy in 61, I believe,
Sounds about right.
to get to the moon and bring a person back, and obviously beat the Soviet Union at the time, and obviously a political stunt,
Yeah.
but supported by the engineering and the science development that goes with that, that they got scared and said, okay, instead of sending Apollo 8 into orbit around the Earth, let's just send it to the moon, go around the moon, and then come back.
Right.
And one of the reasons for that, it was the lunar module, which is not unlike what's happening now, which is the lander to go from lunar orbit to the surface and back up again, was behind in terms of its development.
Right.
And so it wasn't really ready for Apollo 8 mission. And the idea initially was to send it in and low Earth orbit and test it. That happened later with Apollo 9. But let's test, and since we have no lunar orbiter to take into space, what's the point of going?
Right.
So let's go around the moon instead and come back, type of thing, right? Go and orbit around the moon, a few orbits, and then come back. And you test a lot of the rocket engineering that you need, you need to test a motor on the command service module that would light up, that would send you on the translunar ejection orbit. You need to get to the moon, then you need to slow down, so you burn that engine again to get in orbit, captured by the moon's gravity, essentially. Then you need to light up that engine later on to blast, to get out of there and get back towards the Earth. So you got all these different things that need to happen, and plus a spacecraft needs to come in at a good speed, right? When it hits the upper atmosphere, that would be the same kind of thing you'd expect when missions actually land on the moon and return. So there are a lot of different things, engineering tests that had to be performed. So there was a lot of good reason to do that.
Yes.
Of course, what we know now is that the large rocket that the Soviet Union was developing actually failed.
Yeah,
It
blew
blew up on the launch pad. A lot of people got killed, if I remember right.
I'm laughing about it, but yes, a lot of people did.
Yeah, and that was all kept secret, hush hush, until well after the Cold War was over. Anyways, so the United States was ahead and didn't realize it. Now, the thing is, this is kind of like that in the sense that we're going to send 4 astronauts, in this case, to the moon. We're going to loop around the moon and then come back. So on this free trajectory type of orbit, in case there's a problem with the engines, that you still be able to get back to the Earth type of thing, makes it a little bit easier. Now, in this case, we have 3 American astronauts and 1 Canadian astronaut. And you have, as you see there in the picture on the far right, there are 3 men and 1 woman. Now, no women have been to the moon. It's all been men. And that's because a lot of the selection that was done back in the Apollo days was test pilots. And, and it was all women at that time, right? And they did select a core of women astronauts, but really never utilized them at all during the Apollo program. And in fact, the first women went up was during the Space Shuttle program.
Space Shuttle, yeah.
That was the first time. But, times have changed, obviously, right? We don't stay stagnant, hopefully, in society. And hopefully time changes to the better, not the worse.
Right.
You never know nowadays, right? So Artemis 2, as we call it then, is going to then be launched to the moon and go around the moon the first time in over 50 years that will send humans back
with
to the moon.
humans. Yeah.
Yeah, so last time was December of 72. That was the Apollo 17.
Mm-hmm.
So hopefully everything goes well
Yeah.
and everything works. And the next mission, which is Artemis 3, that's the one to land on the moon. We just have to wait for the lander to get built. And we have both
Yeah.
SpaceX and Blue Origin are working towards
Working on
that, and we'll see what happens here.
Now, granted,
yeah.
I'll give them this. That's a lot harder than what it took. That was a large portion of the time for the Apollo projects. Why it was Apollo 11 before they had a working lander. You know, it's not easy to do a rocket-assisted descent because there's no atmosphere.
And the other thing is weight. I mean, you had to have very little mass, right? I mean, the walls of the lunar module are so thin, you could probably punch your way through them if you wanted to.
Right.
And under the vacuum and pressurized condition, of course, they're stronger than that, right? So they could stand up. And Northrop Grumman had and I'm watching, you can see documentaries about the hard time they had trying to develop, right, this sort of spacecraft. And it's hard to do it even in Earth orbit. It's so fragile, right? Even
Right.
the Earth's gravity can distort the structure.
Mm-hmm.
So it was really just a design to fly in space. It was never designed, to fly in the upper atmosphere of the Earth or something like that.
Right.
So, and that's mainly because of the mass, right? There's only so much you had to work with the Saturn V.
So much fuel, so much for...
Yeah, I mean, look at the Apollo 11 when they landed. You always hear that they barely landed with any fuel left for reserve, right?
Right.
Because you only can take so much. Later on, they had the sort of extended lunar modules, right? A little bit more power, so they could take a little bit more fuel and a little bit more heavier payload and stuff. But still, I mean, it is it's a fine line between what you're able to take and what you have to take.
You can get a sense of this from a Hollywood movie, The Martian,
Right,
with
yeah.
Matt Damon. That was one of the things he had to do was throw out a lot of stuff to get the acceleration and the speed necessary to meet up with the ship that was coming back for him. So,
Yeah. Very interesting.
yeah.
Now, some exciting news besides, the manned space program. This is the unmanned, if you like, space
Okay.
program, and this involves astronomy, telescopes. And this is the recent announcement. So last week, I mean, there was like the Super Bowl of astronomy, sometimes it's described as. It was the January meeting, the winter meeting, as we call it, of the American Astronomical Society, AAS. And they typically have two meetings, one in January and one in sort of late May, early June, somewhere around there, depending on what the, year to year type of thing. And, typically you get thousands and thousands and thousands of astronomers worldwide all go to the single spot. In this case, it was in Pasadena, and talk about their latest discovery and what's going on. And what came out of that meeting is announcement, which caught me off guard. I never heard anything about this before, is that Eric and Wendy Schmidt, you might say, who the heck are they? Who the heck are they? Eric was actually the CEO of Google at one point.
Oh, okay. That's who they are.
So you know what he has in his pocket.
A large pocketbook.
Yeah, lots of moolah. Lots of moolah, moolah, moolah. And what do you do with lots of money? Well, you can do things that you can't do without any money.
Yeah.
And one of those things is to build telescopes.
Okay.
So somebody convinced him, or maybe he was interested in astronomy. It'd be interesting to see where all this idea kind of started. The progenitor of the nugget of this thought is to take some of the money and use it to build 4 telescopes and launch them. And all of this to happen in a relatively short period of time, like 3 years.
Wow.
And included with it is a space telescope actually larger than the Hubble Space Telescope.
Considerably larger,
And that's
3.1 meters.
Yes, the artist's drawing that you see there on the far left illustrates that. Now, Lazuli? The Lazuli Space Telescope, 3.1 meters in diameter. So the Hubble Space Telescope is about 2.4 meters in diameter, and this is to be built and launched in 3 years. That's a really fast
That's
turn
turning
from drawing on a.
In fact, I'm hoping they've already got a mirror prepared for it or something.
They must have
because-
something, because to go from a CAD program in your computer to having it in orbit around the Earth, that's a
in
lot of
3
steps
years,
in
that's
between
a
there.
lot of steps.
A lot of steps indeed. And you might wonder, why was the Hubble so small? Well, don't forget the Hubble was designed from the beginning to be launched by the space shuttle, which means inside of the cargo bay.
Right.
And so it had to fit into that limited volume of space. So the maximum mirror that the Hubble could have is 2.4 meters.
Yeah.
And James Webb doesn't have that issue. And it's because they launched it on an unmanned rocket, but they also designed the mirror to be sort of folded up. And then it opened up once it got outside, the rocket body itself. It's not quite accurate, but you can think of it like an umbrella popping open. You can take an umbrella. What size tube do you have to have in terms of its diameter to shove that umbrella in? Not much, right?
Right.
1.5 inches, 2 inches at the most, right? But once you get it out of the tube and it opens up, of course, it could have a span, if you wanted, of several feet, right?
Right.
So imagine designing a mirror for a telescope like that. It opens up like an umbrella.
And let's face it, it was a risk because nobody knew. We hadn't done anything like that before, and nobody knew if it would actually open.
Wasn't there like 274 or so critical parts that had to work right to get the James Webb to open up its mirrors and locked in the right position
Yes.
and fine-tune the focus?
Yes.
And all of it worked. And you're talking about a spacecraft that was cost order, billions and billions of dollars
Right.
at the end of it all. And it all worked. It was a marvel of engineering, I tell you,
It is.
when you think about it. Now, not only are the Schmidts involved in this space telescope, but notice they're also involved in several ground-based telescopes, and not just in the optical. Some of these are optical infrared, but notice there's a radio telescope array that they're putting their money into as well, helping to build. And that's sort of the second panel from the right. So there are a couple different projects which are kind of interesting. Most of them are except for the space telescope, our array, they have multiple sort of detection elements, optical elements.
Right.
And so it's interesting. I mean, we have the one in California, so the Allen Telescope Array. So Allen was named after, I forget his first name.
I don't remember
He
either.
used to be a member of Microsoft,
Okay.
and he passed away, unfortunately, a few years ago. And he was interested in astronomy, so he gave money to build a radio telescope array to help use it for SETI, which we
For
talked
SETI,
about already today. Okay, and so that was never completed to what they initially designed because he didn't give enough money, I guess, over time.
Probably.
And
But
with an array, what you do is it kind of easy. You say, I want to build a 72 element array. You just don't build 72 elements. You build 50. It's a lot cheaper.
Right. And he set them up where they can self-fund because, of course, they they sell time on their telescopes for other projects. So it's not just SETI and listening for alien signals. Other astronomy work is being done there.
Yeah, and in fact, that Allen telescope array is used by other universities to do, if you like, normal, what do you call it that, astronomical research.
Right.
It's not just for SETI work. SETI is also using it as well. I mean, SETI has a history of having time on different telescopes, like in Arecibo when it was not collapsed, and other places. And then astronomers are a little sensitive, and they didn't want people wasting their time looking for a signal. It's almost like the movie Contact.
Right.
If you ever seen that.
Oh, it's not almost. It really
Well,
is.
I'm just being generous here. Being generous a little bit.
Okay.
And so they said, well, you should get your own telescope or get your own private money. And that's essentially what happened in that case. It's all privately supported. It's not like government taxpayer money is going into listening for aliens. It started out that way a little bit in the late, I guess it would be early 80s. And NASA was going to support a program by giving money to build an array, or at least support an existing array, to help do the SETI program. And Congress, some members in Congress, not all of them, didn't like that. They thought it was a big waste of time. You're spending money to look for little green men? No way. We're taking that item out of the budget.
Right.
It was that sort of thing. So what do you do when that happens? You go to private money. So NASA had to get out of the business.
Of looking for alien signals.
Yeah. So anyways, that's what happened there.
Yep. But this is neat, and it looks like at least one of these, the one on the optical telescope array on the left, furthest on the left, looks like it's probably a survey telescope.
Yes.
Going to look at real big sweeps of the sky.
Yeah, so the Allen Telescope Array is named after Paul Allen. That's the name. Right. So he donated over $30 million to the project.
And that would have been like in the 80s, 90s, right?
Yeah, he's co-founder of Microsoft. Bill Gates, of course, being the most famous of all of them. So yeah, that's where they got their seed money to get going on it. And like I said, if you can build, and this is multiple dishes, right? And the more
Right.
dishes you have, the more sensitive you're going to be, the higher resolution you're going to have, all this kind of thing.
Right.
And so if you want to cut back on the amount of money that it would take to complete the project, just cut back on the number of telescope dishes that you need.
Right.
So you can scale it down or up depending on the money. In fact, I think the initial idea was to make a sort of initial array and then hopefully get other
Other people to
other
sign
people
on
involved, and they
expand
would
it.
yeah,
Yeah.
and they would add their certain number of elements and stuff and make the array bigger and bigger and bigger. But it hasn't. I don't think that really
I don't
happened.
think it
but
materialized like they were.
certainly, the universities use it for normal radio telescopes. So,
Yeah.
and it's in Hat Creek area in California, and that's an area the Hat Creek Observatory is located, and it's a special area where it's radio quiet,
Right.
and you
Kind
don't
of
want
like Green Bank in West Virginia.
yes, you don't want people to use their cell phones and even microwave
Even a
ovens.
microwave oven.
ovens turn out to be. Remember the problem with the microwave oven? So they detected these signals. This is in West Virginia for sure, and they wondered, it was all of a sudden you see this burst of radio signals. I'm like, where the heck? What's that coming from? Is that like human made sort of thing? Is it artificial, or is it natural? Like, I mean, if it's
Right.
natural, where's this burst of radio waves coming from? And then if the story goes, if I got it right, then they realized that it was always coming at around the same time, lunchtime.
Mm-hmm.
And what they narrowed it down was it was people who were microwaving their food during their lunch break and not waiting for the timer to shut off. They would just pop and open the door. And when you pop open the door of the microwave before it stops, you get this little bit of leakage out of the microwave oven,
Right.
for a fraction of a second even. And that was being detected by the radio telescope nearby, one of these side lobes that we
Right.
talked about already. So the moral of the story is let the timer finish. Unless you're at risk of burning your house down there, but pop open the door
Then
early.
pop up at the door. Yeah.
It's kind of cool when you think about it. I mean, in general, the microwave ovens are shielded, so the signals can't leak out when it's going. And a test of that, you can put your phone, take a cell phone, have the cell phone on, set it inside your microwave, close the door. Do not, I emphasize, do not turn on the microwave.
Right.
Now try calling your cell phone from another phone outside
It won't
the
happen.
microwave. And it's not going to receive the signal.
Right.
Because it acts like a Faraday cage of the right size that those microwave waves, the signals can't penetrate inside of that microwave oven. And so the signal's not being picked up by the cell phone.
Mm-hmm.
So that allows you to look through the door of the microwave and not, somehow cook your eyes.
Right.
Because optical light can get out because the wavelength's so much smaller than the microwaves, but the microwaves can't. They're larger than the typical size of the opening and the little wire mesh-looking thing that's in the microwave doors. And so you're safe to have a kid, face plant his face on the outside of the microwave door while the microwave is going, and not worry about getting any damage, which people don't understand, but it's the nature of light, electromagnetic radiation.
And been known since the 1800s.
And it's kind of cool when you think
Yeah.
of Maxwell. So nothing new in that case. But yeah, getting back to this issue, so it's really nice to see private people or individuals support science. In fact, if you look at the way, especially in the United States, the way this support in terms of funding is for science,
It's heading that way where we're going to have to.
it seems we're heading that way, that we need to rely more and more on the generosity of individuals rather
which is
than
a bad place to be, but
rather
we won't
than
go into that just
taxpayers as a whole, right? I mean, when people get worried because they look at the national debt and say, look how much money we owe, we
Yeah.
have to cut back. And once you reach that point of saying that and taking that to heart, then something's got to give. You can't support everything.
now. Right.
And I think that's part of this whole process, right? is
Except,
that.
no, well, like I said, we won't get into that.
But that's been drilled in our heads for how many years? That's
Right.
this national debt. It's a terrible thing, and we need to do something about it. I've been hearing that for I don't know how long,
I've been
decades and
hearing that
decades and
since
decades.
the 70s and 80s.
That's what I mean, right?
Yeah.
So when that happens, right, at some point somebody's going to want to do something about it, and that may be part of the issue. What's happening here?
Yeah.
So, anyways, but yeah, so it's nice to see this sort of process happening.
Yep.
Now, moving on to our next story, I thought this was quite interesting. We don't really spend a lot of time thinking or even talking about this, and that's what's going on around us in terms of our place in the galaxy, interstellar space, in the vicinity of our solar system and our sun included, obviously. A lot of times, and the only way that this really comes up a lot is if we talk about like the Voyager spacecraft, that has gone out and is measuring more of the influence of interstellar space than of our own sun, because it's so far from the sun now, well over 100 astronomical units, where an astronomical unit is the average distance between the Earth and the sun. So these spacecraft are way out there. I mean, they're still within the solar system. They're in the outer solar system, but they're feeling more of the influence of the general, if you like, bathe of light coming from the stars in our vicinity that are in the Milky Way. They're more influenced by that than really our sun in some sense. And part of this whole idea is we live in this local bubble that surrounds us for many light years of hot, and because it's hot, we know why it's hot, is because of the ionized gas that it contains. So we know it's hot because it's ionized gas.
Right.
You need hot, high temperature.
And
that is
we know
particles,
that because of its attenuation of radio signals.
We need particles moving at a high rate of speed in order to knock the electrons, one or more electrons out of different atoms and molecules and so on. And so we know the material is ionized, since that requires a certain kinetic energy of motion of these ensemble of particles, so on. That is what we call temperature. But you don't hear a lot about this. And this particular study that has been published recently, if you want to go to the next slide, Robert, it kind of illustrates it. This gives us an idea of what we mean by the local bubble that surrounds, the sun itself. So here, the sun is in the middle of this artist's conception, this drawing. But this drawing is not just an imagination. It's based on data.
Right.
So these are our best guess based on the observation of what it would look like if we could see such a structure.
If you could see, your eye could see
the structure. And one of the things you'll notice there is you have these sort of trail-like features, especially on the right side of the bubble, right side of where the sun is in the middle there. And it almost looks like a trail or a wake. So it's an ionized wake. And scientists have looked at this and concluded that it looks like it's due to the motion of stars that pass, not that close. I mean, if you read the science report of this, it said it passed near the sun. And that's, oh my God, like a few million years ago. It's like, if it got that close, it would have disturbed the Oort cloud, and you have this raining in of all these comets and stuff, right?
Yeah.
Over a certain time period. And then when you actually look at and dig into the details, the close approach was like 30 light years. It's like, that's not really close, and considering that Proxima Centauri, the nearest star to our sun, is about 4 light years away. So 30 light years is still pretty far away from us. But anyway, it did disturb the local bubble, if you like, of interstellar gas around us. And there are effects that you can see, and that's this wake, the trailing of the stars through that material relative to us. And if we go on to the next, you can see sort of an overall diagram of how things are moving in our vicinity. So begs the question is, what's really going on, near our solar system in terms of what's out in the interstellar matter nearby? And here's a good illustration of that. So here's a map of how things are moving. So the blue arrows show you the direction of the different clouds that make up the interstellar matter that's near our sun, relatively speaking. For scale, there you can see on the bottom and on the left side, the distance in light years. So 0 is centered on the sun. So the scale goes out a little bit more than 20 light years in different directions. And the actual yellow arrow that you see there, that indicates the direction of our sun relative to those clouds.
Okay.
And that, of course, the direction of our sun is related to how it's moving in the disk of the Milky Way galaxy, right? That it's in orbit around the center and so on. And if you look carefully, you can even see the position of Alpha Centauri, the triple star system that's closest to our sun. So that's sort of bottom right of the sun itself. So that gives you sort of better perspective of where things are situated. In fact, if you look carefully, you can see the illustration where different, important objects are located, like the Hyades. So you can see that's nearly upwards in this diagram, right? You can see the star Sirius, which is about 8 light years away from us.
Right. Aquila and Eridani and...
Exactly. So you can get a location, kind of map out exactly where we are relative, if you like, to the nearby interstellar matter. And there's even the bottom arrow, notice there to show you the direction of the center of the Milky Way, the galactic center. So it's directly off to the right. And based on that motion then, if you were looking down, now down and up of course don't mean anything in space, but if you're looking down at this slide, then you can see that the sun then is moving, clockwise around the center of the Milky Way. But of course, if you're on the other side of the disk, you'll be moving
Counterclockwise.
counterclockwise.
So I don't like using those terms for direction.
No, those are really can be problematic.
Yeah.
You have to be very careful.
Wonder
Yes.
Goon does have a question,
Yeah.
and basically asking, are these clouds made up of dust or gas or what?
All of that.
Yes.
Yes,
So
interstellar matter.
dust,
it's
gas, and
gas and
plasma.
dust. Yeah, and the gas can be in ionized form, which is the ionized bubble, and depending on where the atoms are located, it can be inside a little bit of a, if you like, a higher density region, and it may not be ionized because it's kind of shielded from the ambient background of
Right.
light, the radiation field. But it's on the surface of grains, dust grains, then it can be full exposure to UV light from other stars.
Right.
So that can make them ionized at that point. So you get the whole mixture. It's not just one phase, right? There's multiple sort of phases to the matter itself.
But, one thing I like pointing out is that, oddly enough, we're in a fairly rarefied, as this was showing, a rarefied bubble.
Yeah, we're on the edge of what we call the local void. Mm-hmm. Right? When you think of where our galaxy is located, and you're thinking inside the galaxy, but if you go to even much larger scale, beyond the Milky Way, so there's different structure at different scales.
Right.
So if you zoom out, you can see this different, thing. I mean, if you zoom out to further, it's what we call the cosmic web, the way that the large-scale distribution of the galaxies themselves. But yeah, you have that distribution. In fact, there are some beautiful James Webb Space Telescope images that were available that were released early on as sort of to show people that it works. And one of them was an image taken of a spiral galaxy. And when you look at the galaxy, so you're looking at it's a face on, so you're looking right at the disk. You see all these sort of bubble-like structures across the disk. And that's just areas carved out by different, groups and collections of stars, OB associations, star clusters, and so on. And you can see where the dust is on the edge, where it's being pushed out by the light.
Right.
It's pretty intricate and pretty cool looking in that sense. The next thing that's happened recently is that Congress has finally got together and decided what would be NASA's budget. So it's making its way. It hasn't been approved yet. Of course, ultimately, it has to be signed by the President of the United States, and he could veto it if he wanted to.
Right.
But one thing that was done was that all the money that we heard that was taken from NASA, and with catastrophic budget cutback, especially on the science part of NASA, that a lot of that has been put back in by Congress.
Okay.
And it's just a matter of seeing if it's going to get approved eventually by the full Congress and then by the President of the United States. And one of the things that was taken out by Congress and not or by the President, by the White House, and not put back in by the subcommittees and so on that they have, right?
Right.
Is the mission going back to Mars to retrieve those samples that Perseverance is laying down on the surface. I think there's like 37 different rock samples and
something like
soil
that.
samples, and you can see the image of them on the far right there, little strips of a few of them that are just laying there ready for us to pick up and bring back to Earth. The problem is the cost of picking up those samples and returning to the Earth is just way too high than what anyone wants to
Is willing
deal
to pay.
with to
Yeah.
pay the bill. And that wasn't well thought out, unfortunately, at the time. But those samples are not going anywhere unless some other country goes there,
Right.
China,
China.
or something like that, and decides to pick them up for them. I was going to say for us, but I'm
Yeah,
sure they
well.
won't give them to us unless we pay them a lot of money for them. But anyways, there was a proposal from NASA to go back to Mars on manned rocket to pick up the samples and then return them back to the Earth. But the money, the design of the whole thing was cumbersome, very, very expensive. And so at that point, it's like anything else. You hope that the government cancels it before you start actually cutting metal and spending money.
Right.
So it was cut at the design phase in that sense. So
And that means it's not going to happen.
and NASA
anytime
even
in the
asked, and this was before the latest administration, the NASA even put out feelers, is there anybody out there that would have a better design that is cheaper to do the same kind of thing? And nobody came forward with anything. There isn't anything. It's extremely expensive.
Yeah.
So who knows how long these samples will be laying on Mars, but eventually, humans will go there or robots and eventually pick them up. And you can see the artist's drawing on the left was to illustrate that we could use like the helicopter that we had on Mars and fly over to these samples and then pick them up. So essentially glorified drones.
Right.
and bring them back to a spot where you have the rocket ready to launch to go back to Earth with the samples, put it inside the rocket somehow, and then return that cargo back to the Earth so we can analyze the material directly.
It's not a bad system.
It's not a
just-
bad, and it's
yeah.
billions of dollars, but there's no human risk here, right?
Right.
It's going to cost more money to actually send humans to Mars and bring them back
Right.
with the samples, but no one was willing to pay out all that money. So until it becomes more cost effective, I think this program is going to stay the way it is now on the shelf, as they say.
Yeah.
Now, the other interesting thing that just came out recently is this paper that was published on the 5th of this month in Nature Astronomy. And you can see the title there, Possible Challenge of Cold and Warm Dark Matter. And they've been plugging the people who've covered this. They exist on some type of dark object, which is, you might say, what is this? But if you go to the next slide, it gives you kind of more of an idea what's going on. So what you see here in this image is gravitational arc-like features from this particular object that's about 11 billion light years away.
Okay.
And these gravitational arcs, so that's the warpage of light due to the fact that space in the vicinity of an object with a mass is not flat, it's highly curved. And it almost like the space that lies between us and the object itself that gets distorted or warped into this arc-like feature acts like a lens. And the analogy I always like to use here is take a champagne glass, make sure it's empty first.
Yeah.
So if there's anything in it, drink it. Then hold it up, so you're looking through the top of the glass towards the stem and towards the bottom of the glass, and then pass it over some light source, maybe a light in the ceiling or something. And when you'll notice as you pass across a light source, you get this arc-like features, circular-like features. That's almost the same thing what's happening here. Of course, it's not glass that's doing the lensing. In this case, it's the curved of space and time, to be more technical here. But from that curvature, you can estimate what is the object that's causing the warpage of space that you're seeing through these gravitational lens features. How massive you have to be. And you see that in this image, in this slide, you have two places marked with an X. And these are the source of the lensing that's happening here, some of the lensing that they're detecting. And you can estimate based on the lensing what is the mass of those objects. And they're on the order of about 1 million solar masses or so. And you'd expect, well, what would have a mass of 1 million solar masses? Well, a black hole, of course.
Right.
So maybe these are just the locations of a couple black holes that you see there in the arc itself. And if you look very carefully, so this is stuff that's, way in the background, and you can see it good because it's these gravitational lensing features, right?
Right.
And when you look very carefully at these objects, it turns out, well, a black hole can explain what they are. That's not a big deal. But the problem is when you look outside of these regions, these locations, these precise spots on the sky, there's nothing there. And you expect to be a disk of material, and that disk of material, which would be outside the event horizon, would emit light.
Right.
And yet there's no light. It's dark.
Okay.
And that's the unusual nature of it. You can measure the density profile from the light you can see in these observations. And you'll find that these density profiles are way too flat.
Interesting.
It's something they haven't seen before. And yet whatever's causing this mystery, this flat profiles, doesn't emit light that you can see these objects directly. And remember, this is outside of the black hole. It's not the black hole itself. That's not a mystery. We observe black holes all the time nowadays.
Yeah.
It's what lies outside the black hole that's
glows.
is different.
Yeah.
And it's something that doesn't emit electromagnetic radiation, yet you can see it on its effect on the surrounding light that you can see coming from stuff.
Interesting.
So that's the dark nature. What is it? Nobody knows. So it's a great mystery. So they're pressing to do follow-up observations with the James Webb Space Telescope and these sort of things. And so these are perfect candidates to do that type of stuff, right?
Yeah.
So you know what the game is. If you find something interesting and cool, you get ground-based observations. Maybe that's how you found it in the first place.
Mm-hmm.
You publish a paper on it, and you say, if we had Hubble Space Telescope, you see where I'm going with it,
Yeah.
or if you had James Webb Space Telescope observations, we'd be able to tell a heck of a lot more about this object than and we wouldn't have to speculate, you see?
Right.
So this is really cool. This is really interesting. When we submit our proposal, please give us time. That's the game they're playing, you see?
Yep.
And in fact, that's the game we all play, including us, if you know what I'm getting at.
I know what you're getting at. Yeah.
And something we won't say here, but the extra bulla was let in on the thing. An extra bulla, if you're listening, we talked to you back in November about this object. We did get Gemini time to observe the object, and we're analyzing the data.
Yeah.
So our proposal was accepted, and we'll say more about it once all the analysis is completed.
Right.
And we're going to write up a paper, so we don't want to go into detail now until that paper is accepted. And once it's done, we will broadcast to the world what it was that we found.
Yeah, or hopefully.
Yeah, so
You know,
we'll
we
see
may
how
be
things go.
broadcasting that we need more time on the telescope.
Oh, we always would broadcast that, Robert. And we need federal funding.
Yeah.
We need money too, you know. But that's how science is done.
Yeah.
That's how it is done. So we're about the end of our time here on this podcast already. That went really fast. Our next podcast then is going to be on January the 20th, so 1 week from today. If you're interested in any of these objects, if you find something really cool and you don't know what it is and you need to do a follow-up observation, it helps if you have
An education.
an education.
Yeah.
And we'll say more about that in a second when we do a quote, but we encourage everybody to get educated, either informally or formally. If you want to get educated formally, one of the best ways to do it is come to the superb place that we are at.
Right.
And that is the University of North Dakota.
Absolutely. And on days like today, the winter isn't that bad. So
It actually was above freezing today.
Yes.
Everything is melting like crazy. So, and here it is in January. It's the January thaw, as we call it, right?
yep.
But come to the University of North Dakota, and if you can't get here physically, we do have lots of online classes that you can take. You know, and if you are able to get here, then come to campus, come see Robert and I, come
Yeah.
visit the College of Arts and Sciences or anywhere else that you like to look at. There's a ton of programs that you can take, and it's a really good university. I really and nice and
enjoy
clean,
my
and
time here. So.
lots of stuff happening.
Yeah.
New buildings going up, a STEM building next door to our building.
Yep.
So we definitely have a modernized campus and getting better all the time. So I highly encourage you to do so. Now, we always leave you with a quote
All right.
at the end of our
And it sounds
podcast.
like this one deals with education.
It does. And
Okay.
it's by somebody who might know a little bit about education. You might have heard of him.
Okay.
His first name is Albert. His last name, Einstein.
Okay. You might know a little bit.
You might know a little bit. So here's a quote from Albert Einstein. Education is not the learning of facts, but the training of the mind to think.
Love it.
And
Absolutely.
with that, please give us a thumbs up. Please subscribe if you haven't subscribed. And please tell all your friends about the Cosmic Pie podcast.
Okay. And I'll slip in an answer to a final question.
Okay.
No, we don't have a heliophysics program, but we do have an astrophysics program. So,
Right.
So anyway, y'all have a good week.
And
We'll
so if
see
you
next time.
and send us email if you have questions like that. Even when we're not on doing the stream, we're still alive and
Yeah.
can still answer email.
Or we'll
So
try.
feel free to do that. So until next time, thank you for watching.
Bye, folks.